Looking at this board, you see all 20 standard trigonometry formulas. At first glance, it feels like a massive exercise in pure memorization. But trigonometry is a study of angles, and angles are simply turns. If you think of angles as turning motions, you don't need to memorize 20 isolated rules. You only need to understand 4 core parent ideas. Everything else is just an inherited trait. This diagram shows parent 1, the circle. Imagine a toy robot walking from the center to the edge of a circle with a radius of 1. Cosine tells us how many steps the robot took sideways, and sine tells us how many steps it took upward. Because these two movements form a right triangle with the radius, you can square them together to get the radius squared. Since the radius is exactly 1, sine squared plus cosine squared equals 1. Trigonometry's most fundamental identity is a direct measurement of a single-angled step within that unit circle. This animation shows parents 2 and 3. We ask a simple question. What happens when we combine two different turning movements, alpha and then beta? To find the total vertical reach of both turns, we look at how the second angle affects the first. The original upward step, sine alpha, is scaled by the second turn's cosine. Meanwhile, the original sideways step, cosine alpha, actually tilts upward because of the second turn's sine. We add these two contributions together to get the sine addition formula. Cautioning. For the horizontal cosine part, there is a catch. When you combine two turns, some of the sideways movement is converted into vertical movement. That contribution gets subtracted from the total. This is why cosine addition uses a minus sign. Paren 4 is the tangent. Tangent compares up to right, meaning you divide sine by cosine. Curious. Now that we have our 4 parents, what happens if that second turn, beta, is exactly identical to the first turn, alpha? This equation displays the sine addition formula we just built. If we make 2 identical turns, we can physically replace every beta in this formula with an alpha. Both pieces of the equation are now exactly the same, sine alpha, cosine alpha. It merges into 2 sine alpha, cosine alpha. We have just created the double angle formula for sine. The cosine double angle formula works the same way. And because we can plug parent 1, our circle equation, back into it, the cosine double angle can be written algebraically in 3 different ways. These complex double angle identities aren't new rules. They're the parent formulas layered on top of themselves. This graph shows a continuous, wave-like sine curve. We are now stepping away from triangles to calculate sine using infinite pieces of calculus. Imagine building a toy. First, we start with a rough guess. We say sine of x is simply equal to x. It matches in the middle, but quickly pulls away from the true wave. To fix the error, we subtract a piece, x cubed divided by 3 factorial. The line bends, hugging the true curve a little further. Every new alternating fraction we add or subtract improves the approximation. By stringing together these infinite polynomial pieces, the straight line transforms to match the sine wave exactly. There's a strict rule here. This infinite series calculation only works if you measure the angles in radians. It breaks if you use degrees. This flowchart maps all 20 formulas from that chalkboard. The unit circle sits at the top, and the logic flows downward into the addition formulas, the double angles, and finally the infinite calculus series. Trigonometry isn't an assortment of isolated rules. It's a sequence of 4 ideas that continuously reshape themselves into everything we've seen.